I think we can get started. So again, welcome everyone. Your host today, Eugenia from ARC. Thank you, of course, for taking the time to join us today and for our Tech Talk, fine-tuning LLMs with declarative ML orchestration. Again, this is part of our engineering job fair brought to you by ARC. We connect great developers with companies around the world. So basically, I would love to learn more about, if you love to get to know more about the companies that are hiring, we are sharing the link in the chat. So make sure that you visit that as well. Today, we will be learning again about fine-tuning LLMs with declarative ML orchestration. And to make sure that you do take advantage of this talk, feel free to drop all your questions for our speaker in the Q&A section, okay? We will answer them by the end of the talk, but make sure that you do use this specific part of the chat. Let's see. So do not worry about making notes immediately. We will send the recording your way. So make sure you enjoy the call. And let's welcome our special guest today. Here with us is Niels. He's the Chief ML Engineer at Union.ai. He helps data science and machine learning practitioners be more productive while doing research in the ML space. So without further ado, Niels, the stage is yours.
Awesome. Thank you, Eugenia. Hi, everyone. I'm super excited to be here today. As Eugenia said, I'm Niels Bantilan. And before I dive into my talk, sort of want to give you a little bit of background on myself, just so you know where I've been and maybe where I'm going. So I'm currently the Chief ML Engineer at Union.ai. Union.ai is a machine learning and data company that's focusing a lot on infrastructure. And as is the subject of this talk, we're gonna learn a little bit about what kind of infrastructure you need to enable a lot of the machine learning workloads that are kind of state of the art and modern workloads today. Before this, I created Pandera, which is an open source data validation tool. I'm also the author of Union.ml, which is a Union.ai open source product. The core maintainer of Flyte, which is also an open source Union.ai product. That's actually a Linux Foundation open source project. And my background is actually in biology and public health. So for all of you out there who don't necessarily have math or CS background, you can learn all this stuff, and there's a lot of educational material out there these days to sort of ramp up on data science and machine learning. I would say my mission these days is to build the tools that practitioners in data and machine learning need to be more productive, more efficient, reason about problems more clearly. So some of you might be here because of maybe the latest machine learning AI hype cycle, which is LLMs. Last year it was diffusion models. Before that it was, I guess, CNNs. But as we know, large language models are really hot right now. However, even if you had access to the model and data sets and maybe some cache to burn on some GPUs, how do you actually know how to set up and configure the infrastructure that you need to actually train or fine-tune models, right? Or even run them for inference? So this is kind of the subject of this talk, and I'm going to kind of slowly start high level and start getting deeper and deeper into maybe lower levels of the stack, and I'll show you a little bit of math, but not too much math. So here's the story. In the beginning, there was model-centric ML. And model-centric ML treated data as static. These tended to be academic research labs that create these amazing data sets, but they're fixed. And the thing that was changing a lot in I don't know, quote unquote, early days, maybe early 2000s, even before that, I guess. But there's a lot of focus on the model architecture, optimization techniques, and so on. I would say we're sort of solidly in the data-centric ML phase of machine learning and AI. So what this means is now, okay, there are models in production in industry and enterprise level, and people realized, hey, the data set is changing, and we can't just assume static data sets. And there are a lot of assumptions in the model-centric ML space that kind of break down, or there's like missing tools that you need to handle the real world and the chaoticness of the real world. So people realize data is very important, data quality is very important, data processing, data cleaning, monitoring, all of this stuff. Like, what is the tool set for that? And I think we're solidly in this space right now. But I think there's something missing, and I've hinted at it already, which is that I don't want to introduce another centrism, right? Like, all of these are important, but I think the thing that's missing is some kind of infrastructure-centric machine learning. And I'll explain what I mean by this throughout this talk. But in a nutshell, this is essentially the compute, the resources, the machines, the hardware that you need to actually run, fit the data and the models in a machine or a set of machines and actually train these things. And so the question I asked earlier about how do you actually reproduce maybe a cool paper or a cool, blog post about fine-tuning an LLM on some like special data set, like how do I actually reproduce that? And I think this is a more or less complete picture of the kind of framework you need, mental framework that is, for how to reason about how do I actually go about reproducing machine learning models. So for the rest of this talk, we're going to talk about sort of 4 key points, and I've broken this talk down into 4 sections, which is maybe expanding a little bit on this idea of what are the pillars of machine learning. Once we understand that, then why fine-tune large language models in the first place? Then how did we get here? So what is the journey from basic NLP models to large language models, and realizing that transformers are a key piece to this? And then finally, I'll take you on a quick journey of fine-tuning large language models with Flyte, which is the tool that I mentioned earlier, which is an open source workflow orchestration tool for data and machine learning. Okay, so the pillars of ML are not just about models and data. There is that infrastructure piece missing. And so if we consider some PyTorch code, right? Here's the model architecture. It's just a toy example, right? So this is a fully connected multi-layer perceptron. Has 3 layers, uses ReLUs over here, and then produces some probability distribution over some set of categories, right? Pretty abstract. You don't know what the data is about, but maybe you can kind of squint and see some hints of like maybe what's going on. Now the model exists in a training loop always. And so the training loop is the thing that defines the model, the data that you want to train on. So in supervised learning, that involves some features and some targets. The target variable is like, say, here's a picture of handwritten digits. The data is the raw pixel values. I want you to learn the mapping between raw pixel values to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 categories. So this is good. If you had the model and the training code, that's a great start for reproducing any given model. But then you need the data as well. So you might define a function. This is just pulling from Torch Vision data sets. You can imagine creating your own data set, but this is the MNIST data set of handwritten digits. And we return, this function returns the training data set and the test data set for evaluating overfitting. So from there, you have your data, you have your model, you have some kind of training entry point that says, okay, I'm loading the model and data into memory, I'm using some device, CPU or GPU, and I'm going to train for some number of epochs. Return some information about the training run, loss, and maybe some accuracy metrics. But now that I have all this code, how do I know it's going to run somewhere, right? So in this happy path case, I know this is going to run on my M2 laptop because my laptop is powerful enough to fit this model. But this is not necessarily the case for large language models that have upwards of, 1 billion, 7 billion, 13, 70 billion, depending on the model you're using, right? So ideally, in the code or somewhere in my code base, maybe a configuration file, a JSON file or something, but maybe like what if in my code I had some way of knowing what the compute resource requirements were of any given piece of my pipeline. So say my data set needs this much CPU and this much memory. The training function actually needs GPUs instead of CPUs and a little bit more, a little bit less memory, maybe 2 nodes, 2 EC2 instances or something like this, right? So it'd be great if we had that annotation. And that annotation is like, okay, but what if there was an actual way to codify and programmatically get those resources when you run this code? And this is the promise of infrastructure as code. And IAC is not new. This has been a very popular concept in DevOps in that field. But I think we want to marry these different fields together, get the best out of the various practices that we've developed over time. So if a model is the car and the data is the fuel, the energy that propels the car forward, then the infrastructure is the roads, the gas stations, the charging stations, all of that stuff that we kind of would maybe not take for granted, but there's all these things ambiently in our environment that makes the car run. And I think up until now, we sort of don't really have the best tools for reasoning about provisioning and documenting the infrastructure needed to train our models. So with these 3 things together, you get the model artifact, your crystal ball, quote unquote, that you'll use to generate predictions and do the cool things you want to do with machine learning. So next I want to tackle why do we want to fine-tune LLMs in the first place? As some of you may know, there's this emerging field of prompt engineering, and I just want to call this out because it's an important kind of fork in the road for any application builder, right? So here's your LLM, takes in a prompt and it produces a response. These can get really fancy. Prompt engineering is when you change the prompt to change the behavior of the response. You're not actually changing the model itself. The model's weights, in this case, are frozen. And maybe you're saying, in your ChatGPT session, you give it a personality so that it can respond in a specific way. Prompt tuning is when you actually change the first layer, the input embedding layer of your large language models, given some fixed K set of tasks. So these tasks can be editing a paper or, I don't know, responding to a question in a certain way. And this technique will actually change the model weights so as to produce the output that you desire. So here you're starting to get into like, actually, if the model is software, you're like changing the code of the model, right? That's expressed as the parameters of the large language model. Now with fine tuning, you're changing the entire stack. So LLMs you can think of as these stacks of transformers, and there are gray areas here, of course, but in the most naive case, you're updating all the weights of the model based on some data set you've gathered. And so purely from the perspective of an application builder, not an ML researcher, right? You are faced with, do I prompt engineer or do I fine tune? And I'm not going to go through this list, but effectively you're trading off kind of convenience and like the ability to do few shot learning, zero shot learning on a fixed model versus, okay, my data set is my application is just so special and unique that the data that this LLM's been trained on is just not quite cutting it. And I've tried a lot of prompt engineering, but now I need to consider fine tuning. So this is sort of a tongue-in-cheek kind of flowchart of when to fine tune versus prompt engineer. And there are like a couple of different perspectives here, but I'm sort of conflating prompt engineering with using, like, say, a hosted closed source large language model versus playing with and fine-tuning a open source one. Of course, that's a conflation. You could prompt engineer on your own open source kind of models. But from this perspective, right, if you care about data privacy, then you either trust the closed source company, or if you don't really trust them, you need to really go down the fine-tuning route. But if you don't, then prompt engineering is the way to go, because fine-tuning is a whole can of worms, and it's the iteration time of prompt engineering is much faster. So you go through this iteration loop. Have you tried really hard? And if you have, then I guess it's time for you to do fine-tuning. The main thing here is that you'll need to ramp up on a lot of machine learning skills if you don't currently have them. And I guess if you don't, there are, I guess, some low-code fine-tuning products out there. I don't have personal experience with any of them. But if you do have ML skills, then quote unquote high code fine-tuning would be the kind of way to go there. If you get your desired output, then great. Ship your application. There will be some maintenance burden here to like maintain this fine-tuning pipeline, which is another downside. And if you don't, I guess you're just gonna have to twiddle your thumbs and just wait for R&D to get better for your particular problem. Another angle of this is, have you even tried prompt engineering in the first place? Maybe that's a more basic question, just because fine-tuning is a lot more resource intensive. And yet another one might be if your data is out of distribution, maybe you're trying to use a large language model for protein folding or some other exotic thing that you know that your base model hasn't been trained on. So roughly speaking, there are three types of fine-tuning. There's basically just continued pre-training, which is just predicting the next token. There's supervised fine-tuning, which is you're taking a specific prompt and you're mapping it to a specific type of response. And then there's reinforcement learning from human feedback. So this takes questions and answers and some human preference of the answers, right? So this is quick rundown of each of these. Obviously, I'm not going to read these out, but this is all just for reference when we share the slides after the talk. Okay, so maybe you found yourself in the fine-tuning category and you've tried a lot of prompt engineering, it's just not working. Now I kind of want to, for those of you who are not super familiar with the history of machine learning or how we got here, I wanted to give you a brief story of just that. So back in the day, which is literally a decade or a little bit more ago, there were bag of words representations for text. And this was a tabular representation where you have a fixed vocabulary and you either indicate 0 or 1, or a count of how many times that word appeared in the sentence, right? So each of these you can think of as a training example, and you're trying to map it to, I don't know, sentiment or something, some task like that. The problem with this model is that you lose ordering, right? So there's no, you just have a table of counts, basically. The next evolution of this idea is word to vec. I think the famous example was man is to woman as king is to, and then the model would say queen. There are some actual caveats to that I won't get into, but the essential idea of this model is you have a neural net or some kind of model that, given some context, produces the middle word in this case. So pineapples are blank and yellow, spiky is the output. Or you flip that around and given a word, you predict its context. So these are two different ways, right? But the problem with this model is that you're basically averaging the context, and each word can have multiple meanings depending on its context. And this was kind of a decent way of doing that, but it didn't actually weigh. You're just basically averaging, or you're finding some projection of the token representations that aren't quite that good, even though you could do algebra on them, which was pretty cool. Then we have recurrent neural nets, and these allow you to actually model sequences, right? So if you have the pineapples are, what is it, spiky and yellow, you have actually a neural net that is able to unfold itself over time and take variable inputs and produce variable outputs. And so this was a big step in not just NLP, but although it was applied there a lot too. The problem with this is that you can't really, I mean, you could model long-term dependencies, but empirically this was a problem. Long sentences, paragraphs, anything longer than that, the model would have a hard time kind of remembering that information. And there were some things like LSTMs and GRUs that helped with this, with the vanishing gradient problem and other related problems. But there was just this overall issue that it's hard to model things in the far past. So now enter attention, which is one of the core modules of the transformers architecture. And just at a high level, you have these things called queries, keys, and values. And you can think of these as learned representations of information that can be passed across the tokens in your sentence, for example. So a query is basically, as the word in the sentence, the water flows through the river bank. If I have the word bank, the query is the representation of the neural net that says, hey, what other words in the sentence should I be paying attention to? So that's a query. The key is essentially the thing that aligns with the query. So if they're similar, then the word bank should pay attention to river a lot. So that's the information of how well the other words align with the word of interest. And then value is the actual information content of the word river in this case. And what happens, the power of attention is that a token in your data set can be represented and re-represented as a function of its context. And so as you go deeper and deeper, you get richer and richer representations for just the exact same word. So now the river flows, the word bank in the river, the water flows through the riverbank. Now in vector space looks very different from the word, the robber stole money from the bank. So the problem with attention is that it requires a lot of memory. And this is kind of where I'm getting to with maybe the approach of fine-tuning models in memory-constrained context. So maybe you don't have a A100 or H100. So next, I want to get into reasoning about how much memory a model actually needs for you to train it. So if you have a model with 100 parameters, and you're using floating point 32, you're going to need 2,000 bytes of memory. If you scale this up to 1 billion parameters, you're going to need 20 gigs of memory. And that's not just for the memory occupied by the parameters. You're going to also need memory for activations, the gradients, and optimizer states. So with an atom optimizer, you would need to store states for momentum and variance. And there are various different tricks to train larger models and to train them faster. And so there's gradient accumulation, there's model parallelism. For training them faster, there are various optimizers that are known to converge more quickly, different schedulers for the learning rate, and data parallelism, where you copy the model across n machines, so you can process batches more quickly. Another one that's relevant for us to start thinking about how do we represent things, the weights and the parameters and the activations a little bit more compactly is, say, mixed precision training, right? So this is where you increase the throughput of your forward pass by representing the parameters and activations as floating point 13, thereby taking half the space. This doesn't quite reduce the memory requirements of our system, because now, for stability reasons, you're going to have to have another copy of your updates and your gradients in floating point 32, because there is a lossy dynamic here with compressing your weights to lower and lower precisions. So the first, I would say, modern state-of-the-art-ish technique that it's been around for a few years, but I think a lot of people still depend on this to train large models on small machines, is called zero redundancy optimization. The main idea here is to shard your model. So instead of copying your model across all of your 4n machines, you shard your model such that each machine only owns a bit of that, a piece of that model, partition of that model. And during forward passes and backward passes, there's like special intercommunication between those nodes to only duplicate what is needed for a particular part of the forward or backwards pass. So this is just to show you another pictorial representation of the different stages of zero parallelism. There's versions where you only shard the optimizer state, since that's the most expensive memory-wise. And then stage 3 would be sharding all model states. So I'm just going to hop around this video, but to give you an intuition of how this actually works, right? So we have our data and we're partitioning it, we're batching it across our 4 GPUs in this case. And we are, instead of copying all of the model states across all of the 4 available machines, we actually shard them. So this piece is owned by GPU 0, this piece is owned by GPU 1, and so on. And during the forward pass, you only copy over what is absolutely needed for this first. So each of these you can think of as a layer in the neural network, right? So for this first layer, we're just copying over this first part. So you're doing some copying, but you're overall, you're saving on a lot of memory. And if we fast forward, this process just repeats. So you just copy what's needed, and in the backwards passes, you do the same with the optimizer states until you have, your model weight updates. So once you have your model weight updates, you basically send them to the owner of that piece of the model, and you update your model. And at the end, you have a global update. So I know that was super fast. Hopefully you got a sense, kind of high level, how zero works. The next topic I want to get into is 8-bit quantization. And I was going to get to notebook sidebar, but I think I'll need more time. So essentially, quantization is trading off memory for precision. So if you have a 32-bit floating point, you could represent it as an 8-bit integer, but then you're losing all of these digits, and these might be important for the model's learning. So the problem is that quantization doesn't not deal with outliers very well. And 8-bit optimizers via blockwise quantization is a very interesting paper that allows you to deal with this outlier problem so that you can actually represent your model in fewer and fewer bits, in this case 8 bits. Won't get into the details here. But the conclusion and the reason why you do this is you can actually save a lot of memory, and you essentially have the same kind of training profile loss curves here. So the last technique I'll show you before hopping onto the rest of the fine-tuning journey on Flyte is low-rank adaptation. So to understand this technique, let's first consider how weight updates actually happen in a neural net. So you have some weights, you do backpropagation, and you end up with delta W, which is the weight updates. And you simply add them together to get your updated model, W prime. So doing a forward pass with a new model is H equals W prime X. So that's H is your new prediction. But what LoRA does is it decomposes this. So it keeps them decomposed. So H equals W prime X, oops, this plus shouldn't be here, is equivalent to WX plus delta WX. Now, in this case, I'm duplicating my weights, which kind of sucks. So, you're increasing the memory and compute requirements of your system. So why would you do this? Well, there's a trick you can do, which is you can decompose the weight update into two smaller matrices, right? So delta W equals WA times WB. And as long as the dimensionalities add up or sort of align such that when you multiply these two things, you get the original dimensionality of W, you should be good. So this allows you to reformulate the situation into WX plus WA times WB times X. I won't get into this R too much. I do dedicate a slide to it, but essentially you can think of this as model capacity. So the smaller your R, the more memory you'll save, but the less model capacity you'll have. So the intuition is that during pre-training, your large language model actually needs all of those weights because you're modeling internet scale data. But when you're fine-tuning on a specific task, a lot of those columns are actually redundant. The columns in your matrix, or rows and columns in your matrix, are redundant such that you actually don't need all those parameters. So by specifying a lower rank, you'll actually, learn just fine, right? And so that is demonstrated in the LoRA paper, because here they did full fine-tuning and they pretty much got equivalent accuracies on certain data sets. Another notebook sidebar I won't get into, but here this goes into a notebook that you can play around with if you're curious. Is actually a very basic LoRA implementation. So the last thing I'll say here is there's a kind of a new kid on the block, QLoRA, which is quantized low rank adaptation. And the main differences are that you represent your LoRA weights and your base model in 4-bit normal float representation. You perform double quantization, which I don't have too much time to explain, but you quantize the quantization constants. So happy to chat about that after this. then you also page your optimizer states to CPU to handle kind of memory spikes during training. Okay, so in the next 10, 15 minutes, I'm going to take you through a fine-tuning journey of the Llama 2 model on Flyte. So just to remind you of the different kinds of fine-tuning, roughly speaking, the code and the slides I'll show you are focusing basically just on continued pre-training and supervised fine-tuning. And so the two workflows that we're going to build are essentially taking the Wikipedia or a subset of the Wikipedia dataset and just doing next token prediction using Llama 2 and 0. We're going to quantize that model and publish both models to Hugging Face Hub. And then for the supervised fine-tuning workflow, we're just going to take the alpaca dataset, which is a set of actually AI-generated prompt responses, and fine-tune the Llama 2 model on those prompt response pairs. So for the CPT workflow, essentially, the training code kind of looks like this. This is obviously an abbreviation, but just as I showed you earlier, right? This is the data set, splitting the data set into train and evaluation sets, grabbing the model, training it, and saving it, right? So this is using the Hugging Face Transformers library, amazing library for transformers. All the data is doing, we could ignore a lot of this validation stuff, although it is important, but we're just loading the Wikipedia data set and validating it, then passing it to the next task, which is the training function. In our case, the training entry point will be this kind of entry point function that gets the data, passes it into a training function, quantizes it, and then saves the base model and the quantized model into Hugging Face. So what is the infrastructure that actually runs this? You can see here we're importing FlyteKit, the task and workflow decorators from FlyteKit. And what FlyteKit gives you is a functional way of defining, okay, for the get data task, I only need 2 CPUs and 8 gigs of memory. But for the training task, I actually want to automatically retry on failure. I want to cache the model if I pass it the same exact inputs. And I want to grab some resources for this, which is I want a machine with 8 GPUs, 64 CPUs, 256 gigs of memory, some ephemeral storage. And I actually want to do distributed training. And so this elastic class here is a configuration that tells Flyte, hey, I actually want 5 nodes of this system requirement. And I'm going to run 8 processes per node for each 1 process per GPU. And this plugin actually will run the function body code using torchrun, which is the distributed training framework exposed by PyTorch. And then to stitch everything together, I'm going to define this @workflow decorator for my fine-tune function. And this is basically the DAG builder that Flyte gives you, which is, if we hop back here, the way you stitch together different tasks to achieve some more complex set of computations. So I'll do a quick demo of this. And hopefully the demo gods are okay today. So this is the fine-tuning code that I just showed you. I'm not going to go through this entire script, but I can effectively ship this code to my Flyte cluster, which is a whole another can of worms. But I can invoke pyflyte run, and essentially I use a configuration file to point it to some endpoint, right? So maybe I can show you what this looks like, right? So this just points to a Flyte cluster that I already have running. And I give it a pre-built image. So this is a Docker image that I've built just for the purposes of this demo that contains all of my dependencies. And I'm pointing it to this LLM fine-tuning script targeting the fine-tuning workflow that I have here in the bottom. And I'm passing it the config for training, so like how many epochs, so on and so forth, and the deep speed configuration that I'm using. So deep speed is a framework that allows you to leverage the zero redundancy framework quite easily. So if I run this command, essentially what's happening is it's packaging up the code, sending it over to the Flyte cluster, authenticating, obviously, first. And it's going to spit out a link that if I visit, actually is my workflow that's already completed because I've pre-cached all the steps, right? So the original workflow for this is actually back here. So this is the Flyte UI, and it allows you to visualize what exactly is going on in your workflow. And as you can see here, here's the DAG. Here's the timeline view of how long each step took. Obviously, the training step took the longest. And I've actually hooked this up to weights and biases. So I can actually go into weights and biases for more granular training metrics. And we can see here that I'm not collecting much, just a training loss. And we see it, happily going down. So that was the continued pre-training setting where we were fine-tuning just on the Wikipedia dataset subset. Now, I just trained the 7 billion parameter llama model, right? What if I want to fit the 70 billion parameter one? So what I'm going to run is the QLoRA training script for this, which uses QLoRA and a bunch of other tricks to really be able to pack in as large a model as possible on essentially 8 T4 GPUs. So if I run this, I'm actually using a different cluster. I'm using a Union Cloud-backed Flyte cluster. And we wait for a few seconds. Hopefully this will go through. Awesome. So this is kicking off a new execution. You see the UI is slightly different because this is Union Cloud. Guess shameless pitch, Union Cloud is the managed version of Flyte. But I already have one cooking for you here. So it's been running for about an hour and 20 minutes. And if we hop onto the weights and biases trace here, we can see that it's a 7 billion parameter model being trained on very small GPUs. And so there's going to be a trade-off here of time it takes to train, right? But just to show you that it is possible. One thing I would like to point out here is looking at your metrics. So, and this is a good tip for any kind of platform you're using, right? But obviously, I'm not fully utilizing my hardware, so I could probably increase my batch size. But one thing that's interesting here is to be careful about this GPU utilization metric. I think weights and biases averages 15 seconds worth of this metric. So it looks like I'm totally underutilizing my GPUs. But if I hop onto the Union Cloud utilization dashboard, we actually see what's happening here. So what I'm doing is I've sharded the model across all 8 GPUs, right? So this is model parallelism, not data parallelism. And so this is, we're using the GPUs at 100%, but because they're intercommunicating and passing model state and data between the different layers of the shards, we're seeing this very spiky behavior. So that's Flyte in a nutshell. essentially you can declaratively say what resources you need for a particular task. Flyte, which is built up on top of Kubernetes, will find the necessary resources for you, provision those resources, and run your code in the cloud. So this can be set up on AWS or GCP or Azure. Okay, so I won't go through the rest of the Flyte slides, but I did want to give you an overview of what exactly happened. So first we defined our tasks and our workflows locally. And when I ran PyFlyte run, we actually packaged and registered all of that code, all of its dependencies onto a Flyte cluster. And that Flyte cluster manages the scheduling and when things run how, and uses Kubernetes to run each task on its own pod. And this is another talk, so I'm gonna skip ahead really to the end, which is that the main takeaway that I want you to remember from this talk is that models are not just the models and data. And I think that may be obvious, but worth calling out. The model is actually a combination of model data and the infrastructure that produced it. And so with that, I want to end on this resources slide. Want to thank you for your attention. I'm happy to answer any questions that came up. This is the Flyte website if you're curious about learning more, the docs, and then the 3 notebooks that I didn't have really much time to get into. So thanks so much.
Thank you, Niels. Great. So thank you so much. This was really a great talk. We do want to have a few minutes to answer some questions. I can see that you have already put them in the chat. Let's see if we have time to answer more. So if you have any others, feel free to add them. But let's jump right in. Our first question comes from Carlos. He says that he also comes from a non-traditional background and has a heavy STEM background similar to yours. So he would like to know what resources would you recommend to get started in AI ML work. He has 2 years of full stack experience and wants to make himself more hireable for the AI sector. Oh, I think you are muted.
Oh, yes, okay. Yeah, so this is a great question. So now with, I think, LLMs and generative AI, it's interesting because depending on what you want to do, they're like kind of roughly there's a fork in the road. So you can either go sort of what is being called AI engineer now, and not a big fan of the name just because AI, ML, they're like essentially synonyms. And then anyway, that's all. Don't want to get into that. But essentially, AI engineers treat ML models as functions, either as a service, an API call, or a function call. And they embed it into a larger system that looks a lot more like a typical full stack kind of application that we see today. So in that case, you would want to learn a little bit about ML and how embeddings work and how to use vector databases and how do you efficiently search, match a query to like some set of documents that you've previously embedded, things like this, right? So you're using LLMs or generative AI as a function, and you're not necessarily training it, right? So that's a path that's totally opened up now with the recent developments. To get into training models, I can really only speak to my experience, sort of what I started almost 10 years ago, which is Coursera and like textbooks and YouTube videos. And like, for me personally, right, like I didn't have much math confidence. So Khan Academy actually was a huge booster of just like, oh yeah, I can understand this stuff and kind of do it. So there's the learning aspect. but then there's the building aspect as well of your learnings are going to go away if you don't build something with those learnings. And it doesn't have to be, million GitHub star project, right? It can be like a small thing that you build for yourself to reinforce those learnings. But then, to the hireability point, it gets you kind of a trail of like receipts of things that you've done and things that you've built. I kind of want to say I don't want to push for sort of like always hacking, even on your free time, kind of sacrificing life. I'm very much a fan of, doing other stuff like hiking and I don't know, playing an instrument or something, right? But yeah, these are important things to sort of to do to ramp up and stick out, I guess, in the very competitive space.
Great. Thank you. Let's move over to Gerardo's question. He wants to know what is the difference between embedding RAGs and fine tuning?
Yeah, so embeddings and retrieval augmented generation is kind of like that AI engineer bucket that I mentioned earlier, right? So you're using the LLM as a function. And what that function, input to that function is text. The output can be more text or embeddings. So it's like, I guess, polymorphic. You can do different things with it depending on the input. But like RAG is essentially engineering around assuming that your model is fixed, the model weights are fixed. Whereas fine tuning is you're taking some custom data set that you might have created and you're actually doing forward and backward passes through it to like update the weights of that model. So if you think about the software 2.0 kind of paradigm popularized by Andrej Karpathy, it's sort of the LLM is code expressed as a bunch of just a pile of numbers. And to update that code, you actually need to create a data set that changes that code in some way so as to optimize for the task you're interested in.
Awesome. So thank you again. Well, I don't think we will have time to run over all of this. Just so you know, you can reach out to Niels afterwards on social. We do have a few minutes, so let's go with Oleg's question. He asked if it would be advisable to take proximal policy optimization into account and vector databases.
Yeah, from my understanding, I don't have a super deep understanding on the RL side of this, but from my understanding, PPO is a type of framework for doing RL that predates LLMs. I think the main idea is you don't want to update your model in such a way that it veers too much from the policy you already have. I guess if you get so deep that you're thinking about these questions, yeah, it is important to take into account. I think the other framework is direct preference optimization, DPO, and there are probably more I'm not aware of. Vector DBs, that's more in the space of how do I retrieve. It's like information retrieval with LLM representations. So here's like my company's legal documents. I embed them into this vector database. I chat with my documents. So I ask a query, and then that query needs to like retrieve some set of documents so as to, reduce the search space. Yeah.
Great. Awesome. So let's see. As for Joel, he wants to know now that GPT 3.5 for fine tuning has been released, will it be a little less useful to use vector DB with embedding for AI applications that need a context?
That's a great question. I don't know is the honest response. Fine tuning is finicky because this is a problem in ML in general, right? Is like updates can be catastrophic potentially. I'm assuming OpenAI will handle abstract away a lot of the issues that come with model training, but I think it's all about like cost and iteration cycles. I don't know how much it costs to fine tune on OpenAI, but fine tuning is just more expensive um, for the reasons maybe that you saw in this talk. Whereas using a vector DB, enriching your prompt with some extra context, it's fairly cheap because inference is cheaper than training. And I think that's so. I don't know if there's a very principled way of figuring this out. A lot of it, I think, is still Wild West, and you kind of just have to try it out on your application. But as I said earlier in my talk, prompt engineering for an application builder is almost always the way to go first.
Great. Thank you. I can see that Orlando's asking about the time where this is going to be available for you to watch. Just so you know, it should be uploaded in about 2 to 3 days. Just as a reminder, also Niels shared the slides on the chat, so make sure you click on those as well before ending. And just let's have one last question. This is going to come from Naren. He wants to know, were there any comparisons with the model sharding versus not sharding the model? This is in terms of the GPU utilization example for one. If there are other metrics, he is curious.
Yeah, I think there are a couple metrics to tune or to care about when working with GPUs, which is pretty much all the ones that weights and biases exposes, right? So it's how much memory, GPU memory, have you allocated? So if that's below 100, you can probably either fit a larger model or more data points, increase batch size. There's a throughput, right? So like, is your GPU actually using its processors to crunch all those numbers? And then there's how much time is being spent reading data into GPU memory. So in terms of like going back to this sharding versus not sharding question, I think that it's there's not a good solution for trying to figure out what exact setup you need for your exact like hardware and model that you want to train. I think Hugging Face recently came up with one. I forget what it's called. You could probably Google it, but the main comparison here is that if you have too big of a model that can't fit on one GPU, you will just have to shard it across like 4 or whatever, right? So I think the trade-off there is runtime, right? Because you incur by sharding a model across multiple devices, you then have to do some network communication over the devices, or you have to write some intermediary place, and then read into the next device if you're like passing activations or something like this, right? So it's sort of, sorry, there's not a great answer to the question. I'm not sure if I can really address it, but sharding versus not sharding is like, will the model fit at all? And if not, you're just going to have to shard. And what is the runtime cost overhead of doing so?
Thank you. Thank you so much, Niels. So due to time, we are going to wrap up the tech talk here. If we didn't get to your question, feel free to reach out to Niels after the talk. We have shared in the chat his social. However, in order to end this on a great note, I would like to ask you a question that we ask all of our special guests. And this would be, what's your one piece of advice that you wish you had known 1 year ago?
Oh, 1 year ago. Huh. When was that? August. I forget what I was doing. Let's see. I can't think of quite a great answer for this. I think
let's make it a few years back.
Few years. Maybe. Okay, great. I think this is going to be very biased, obviously, but it was only a few years ago that I started actually caring about the lower level workings of things, right, in machine learning, right? So I sort of built up knowledge in some math and then essentially just like got comfortable. I became happy kind of abstracting all of this away and just started using frameworks, right? sklearn or PyTorch or, whatever else. And frameworks are great. I mean, there's a reason they exist. But I think if you become interested in sort of how to optimize things and how to debug things, it becomes really important to learn a little bit about hardware, a little bit more like CSE stuff that I was not trained in classically. So thinking about floating point representations, thinking about how GPUs work, this is still honestly an ongoing journey for me, right? So, but just taking that step to like care and feeling the pain of not being able to debug something because you're just using a higher level framework and you're like the buck stops there. There's like literally nothing you can do besides maybe read some code and like open a PR to the open source framework, right? So there's caring about the lower level stuff and then getting comfortable faster reading other people's code.
Great. So thank you very much, Niels, once again. That's a wrap, everyone. Thank you all so much for joining. We have learned very helpful advice from our speaker today. This is the end of our chat, but again, as I mentioned, go follow Niels on their social media. We have left everything on the comment box. If you enjoyed the session and you want to learn more about the companies that are hiring, we have pinned the link in the chat as well. And yeah, again, I can see that there were a few questions. The recordings will be shared in a few days. And also, I think Niels left the Union.ai career board, just in case you want to go check that out. So thank you again, and see you soon.
Thanks, everyone. Bye.
Bye-bye.